Hello and welcome to this session of ACS Science Talks, Connecting the World Through Science. This is the virtual lecture series, Scientific Talks by specialists on specialized topics for a specialized audience. I'm Kunal Gupta and I'm pleased to be a host for today's broadcast of ACS Science Talks. Our speaker for today is Professor Stefanie Dehnen. Professor Dehnen received her diploma in chemistry from Karlsruhe Institute of Technology in 1993 and her PhD degree in chemistry from KIT in 1996 under the guidance of Professor Dieter Fenz. She served as a researcher and lecturer at KIT from 1998 to 2005 and subsequently from 2006 as Professor of Inorganic Chemistry at Philipps University of Marburg, where she also had roles as Executive Director of the Scientific Center of Material Science and Dean of the Department of Chemistry. In September 2022, Professor Dehnen returned to KIT as Professor in Information-Based Materials Design and Nanoscience and the Executive Director of the Institute of Nanotechnology. Professor Dehnen has been a recipient of multiple awards, which includes the Waller Young Scientist Award from German Chemical Society, State of Baden-Württemberg Teaching Award, Philipps University of Marburg Award for Support of Women in Science, Alfred Stock Memorial Award from the German Chemical Society, and in 2022, she was awarded the Gottfried Wilhelm Leibniz Prize from the DFG, the highest German-based research award. She currently serves as the editor-in-chief of ACS journal Inorganic Chemistry. Professor Dehnen is the first European-based and first female editor-in-chief for the journal. Thank you, Professor Dehnen, for joining us. The stage is all yours.
Thank you very much for the very kind introduction and for giving me the opportunity to share a little bit of our chemistry in addition to my editorial activity, which I'm enjoying every day. So besides of having fun with the editorial work I'm doing every day, I'm a chemist and I'm doing inorganic chemistry and I'm doing chemistry in the field of cluster chemistry. And this is what I'm going to talk about today, about multinary clusters. And I give you a broad overview about our work that is in the field of these kinds of materials and species, which we would call atomically precise materials. And you will see that they can have very uncommon properties. So the challenges that we have to tackle today all together, I think this is something that all chemists are joining, is to somehow meet the sustainability development goals of the United Nations, which you can see in a very small manner. I think I take the laser pointer. Can you see my laser pointer? You can probably. On the right-hand side, I don't want to show them in a larger mode. You probably know about them, but I tell you what materials chemistry, in particular chemistry in general, can contribute. And here is a number of examples. So you see climate, you see responsible consumption, you see clean water, and so on and so forth. And so something has to be done here, and materials can be very instrumental in terms of catalysis, gas storage, or energy conversion, for example. So we need new materials. This is one of the goals we have to tackle, and it's very essential to have innovative and also sustainable functional materials. A second thing is that we have to think about effective design of such materials and clean preparation methods, which gives us at hand what we have to do every day in our labs. And so the title of my talk was Atomically Precise Materials with Uncommon Properties. And I'd like to show you somehow in which way we are trying to contribute to these ideas, to have innovative new materials and to try and have sustainable preparation methods for them. Before I start with the actual science in this work, I'd like to outline what multinary clusters are, why we are talking about them, how we are doing them, and I'd like to start out with the word cluster itself. So what a cluster is may be known to many of you, but maybe some don't. So this is why I'm letting you have a view at this slide. And you see a couple of clusters on that slide here, some examples of them, and they are in a size regime of maybe 0.5 nanometer to 3 nanometers. And so they are situated in between the size of very small molecules like these complexes on the left-hand side and nanoparticles on the right-hand side, and finally bulk materials. These small molecules and cluster molecules have something in common, and this is that they are atomically precise and they are monodispersed. So once you form a compound comprising these kind of molecules, you'll have a certain definition of a molecular size, and you can count the atoms and you know where they are sitting in this material. This is different from nanoparticles, where you should rather draw cartoons when you would like to outline the atomic positions. So they have different properties. They are much larger in scale, and they are also more towards the bulk materials in some regards. They are somewhere in between, but this atomic precision is reserved for the cluster materials. The original definition of a cluster materials dates back to the 1960s when Al Cotton defined a cluster as being a molecule that comprises at least 3 metal atoms. And this actually is the seminal first work in this field. And he said that they should have direct metal-metal bonds to represent a cluster molecule. Today, the definition of a cluster is much broader. So you will talk about a cluster if it's purely made up of metals, or if it's also purely made up of non-metals like fullerenes, could be called a cluster, or boranes, if you will. And they can also be both in one. They can be non-metal bridged metal clusters like these ones here. You'll see this in different colors of the atoms drawn in this cartoons. So a cluster is something that has a certain size and has to be atomically precise. This is roughly what we need as a precondition. And so owing to this broad variety, you can also have all kinds of bonding interactions. They can be more metallic, they can be rather covalent or only covalent, they can be ionic or dispersive. And of course, the clusters can be unprotected. For example, this fullerene one, or here's an anion that can have just charges or counter ions, but they can also have a ligand shell that protects them from further growth, for example. And along with the interactions and the compositions here, you can have clusters that are homoatomic in nature, or have 2 different types of atoms, 3 different types of atoms, or just multinary, because they have a different variety of different atoms in them. And so this is how we would define a cluster molecule today, so rather broad definition. And the question is why we are interested in those materials. So what is special about clusters? And here are 3 very broad and rough reasons for it, but you can summarize them as follows. So one is the syntactic challenge. You want the cluster molecule to stop in growth at this point. You don't want it to fall apart to form the precursors maybe, or don't want them to grow further into nanoparticles or the bulk. So this is a challenge, and so something like the art of synthesis behind this idea. Second, most of cluster molecules that have been reported have very interesting structures and in many cases uncommon bonding modes, which also cause different properties than, for example, small molecules will come up with. And there are also some potential uses inside. Cluster molecules are not really regularly used so far, but it's close to some real applications. And I'll talk about that a little bit later as well. The last question about this introduction would be how these clusters are formed. And to start right away, there are hundreds, if not more, different methods to approach cluster molecules. And I'd like to just introduce briefly how we are doing multinary clusters. And we are starting out using the whole periodic table. And this is something that also defines the beauty of inorganic chemistry, that you can deal with pretty much all of the elements that we have in our periodic table. And what we are doing and specifically is that we use binary aggregates of p-block elements, like the combination of group 14 and 16 elements, in such small precursor molecules. We can also use different combinations like group 13 and 15 or group 14 and 15. So everything else excluding the chalcogenes, as you can see here. And these type of precursor molecules are then combined with something else, for example, with a D or F block element, metal atom or metal ion or complex. And this way form cluster molecules of a multinary or you can say multinary composition. They can have different shapes, of course. Here are just 2 on my slide. And you can also continue with another type of modification. Instead of modifying the atomic composition, you can just replace one of the chalcogen ligands in this precursor molecule with an organic group, and this way reach out and toward clusters that have an organic shielding on them. And these clusters can then be treated in similar ways. So one possibility is expanding the inorganic core by adding D-block metals, for example, or using a functional group of the organic group and react this with another organic molecule to expand the organic ligand shell. And so this gives you a lot of varieties of how to use these clusters in further follow-up chemistry. So to summarize, we are using a kind of bottom-up approach from small molecules toward the multinary cluster molecules we are heading toward. And the reason why we are going this way, instead of just throwing things together, for example, in a one-pot reaction, but using specifically these binary precursor molecules, is that this allows us for a very controlled combination of properties. We know the properties of these precursor or the combinations, the elemental combinations pretty well, and then we can try and control it during cluster growth. Second, this way we can try and fine-tune the geometric and electronic structures of these compounds. You can see this from different colors, for example. And overall, this is a pretty mild approach because it's type of coordination chemical approach where you use these molecules that you can also understand as kind of ligands, for example, to a transition metal, and then do this in solution instead of, for example, doing high temperature solid state chemistry. So this is a brief overview of how we're approaching our compounds, because I won't detail that too much during my talk. However, this way we get into different families of cluster compounds to expand the group 14-16 elemental combinations. And here we get into so-called chalcogenidometalates. This can be rather classical if you use classical ways. That means, for example, reactions in protic solvents or even solid state reactions would go to this way. Or you use a non-classical approach. This is a so-called ionothermal approach, and I'll do this a bit more, and you will get to very, very uncommon structures this way. When replacing one of the chalcogen ligands with an organic group, the products will be hybrid in nature. And so what we are looking at here is so-called multifunctionality, or also molecular containments. This combination of inorganic and organic parts produce in how they play together. And last but not least, with another elemental combination, which is just metallic or semi-metallic, so excluding the chalcogenes, you will have something like multi-metallic clusters. And these are so-called Sintel clusters or Sintel polyanions. And here, this field is pretty young. And so the formation pathways and the bonding and reactivity in these compounds is still something we're interested about. I won't talk too much about this part here. I will rather concentrate on that side, yet would like to give you just a little taste of what this chemistry is about and introduce a bit the work that we are doing here. So this kind of precursors are called Sintel anions. These are metal-light anions. Maybe I just go back for a second to outline that here are oxidation states, formal oxidation states on that slide, saying that these are metallates. Here, the oxidation state of the metal atoms involved are negative, so that gives them the nature of a metal-lite. And they are isoelectronic, not only in structure, but also in electronic numbers, with phosphorus or arsenic in the P4 and AS4 modifications. And this is easily understood if you look at the charges. So in this element modifications, the charges per atom is 0, and you can give a group 14 element a negative charge, which makes it a pseudo group 15 element by just having the same number of valence electrons. The same can be done with group 13 elements. If we give it 2 charges, it will have the same electron number as a group 15 element, and so being a pseudo group 15 element. But then you add charges, of course, to this assembly, because you need to have the electrons somewhere, but both are isoelectronic and have the same bonding properties in this regard. So this gives it a chemistry, or makes this chemistry related at least to the chemistry that has been done for many years with white phosphorus and yellow arsenic. But of course, the charges add a difference to it. You can also use these and react it with, for example, D or F block atoms or ions, and then you will have some further expansion of these molecules. The same can be thought to be done with pure Sintel anions of just one element. So give all of these atoms a charge and we'll have the same electron number as phosphorus. Yet these are very, very poorly soluble, since each atom has a charge, and this is a very high charge for this little molecule. So this is not so convenient for use. Yet these two have in common that they are called Sintel anions. And here two important names have to be mentioned. One is the name of Eduard Sintel himself. He was the first one to recognize that metal atoms can assemble in anionic molecules, so the so-called Sintel anions. The second name to be mentioned is that of John Corbett, who was the first one to add krypton molecules to sequester the counter ions for these anions. And this helped that in those days to form the first crystals and elucidate the crystal structures. And we are still using krypton in our chemistry today for forming crystals in most cases. And here is a just brief overview of what happens if we use these binary Sintel anions with these lower charges, just 2 charges, with a diversity of elemental combinations. The blue and the red is the elemental combination of this tetrahedron, and the pink is a D block element, the green is an F or F block element, and you see that there's a variety of different structures popping up if you do these reactions in solution. And this variety is difficult to understand. Why is it exactly this cluster to form? But it's reproducible, and all of them are multimetallic, so-called multimetallic or Sinter clusters. And we can then analyze their bonding modes, for example. We can also, now this is stopping for a second. Let me see whether I get further. Yeah, we can ask ourselves about the formation of these clusters, which, as I said, is not really obvious. And if you use this tetrahedral unit and get into non-tetrahedral cages, you will ask yourself how that goes. In this example, it's pretty simple because you have tetrahedral ligand type units on your coordination compound or cluster, but in all other cases you need to do some kind of fragmentation, rearrangement, and so on. And we've been lucky in the combination of germanium, arsenic, and a group 5 metal that we could find some key intermediate, which is this one, that told us the whole formation cascade until these larger clusters, which for the last step required the use of genetic algorithm studies, so we had to use a digital twin here. But these are all crystal structures, and we could tell how these little tetrahedra form these more complicated cluster molecules. The reactivity is also something we're interested in, and actually it's possible to show that some clusters in which the D block metal, for example, is situated on the cluster surface can release an organic ligand, and then this gives rise to the activity in bond activation for small molecules. And more recently, we found out that we can also form this kind of cluster molecules also with ruthenium atom at the surfaces, and these showed us via calculations that we have a new type of metal aromaticity, and I will briefly mention that during my talk. And we are interested in these kinds of very uncommon bonding modes here. So this is pretty much all I'd like to show you about the Sinter chemistry in general. I will get back with one or a couple of slides during my talk about other chemistry or other cluster molecules. And this is my outline for the main part of the talk, which I'll be dedicating to the group 14-16 chemistry. And here one focus will be soluble semiconductor clusters, and a second, a very brief focus will be a new white light emitters. Let's start out with the first one. So as I told you, we can use these precursor molecules and put them into ionic liquids to do so-called ionothermal approach and find very uncommon structures. And we use either these small tetrahedra or we use larger. So these are so-called super tetrahedra as precursor materials. So you'll see a little bit more than just these little tetrahedra today. And we use ionic liquids for it. Ionic liquids are just salts with very low melting points, like below 100 degrees C. And this gives them a character as a so-called designer solvent. So because you can use different kinds of cations, different kinds of anions to form this ionic liquid, the only precondition is that this the salt structure must be very bad. So it doesn't want to crystallize, and this is why it's melting at so low temperatures. And here you can see just a movement from my lab. So these ionic liquids viscose liquids, and you can do chemistry in them like in solvents, and they can have different colors and different viscosities and so on. And one of these, or one type of ionic liquids is imidazolium based, and this is what we are using all the time with a variety of different counter ions. And then you put them into ampules, heat them for some days, and this is what is summarized as ionothermal reactions. And if you're lucky, you get nice single crystals out of these reactions. So what you're doing is some kind of a solid state synthesis near room temperature. At least in the, from the viewpoint of a solid state chemist, this is near room temperature. You won't probably use your fingers to test the temperature, but it's still pretty low in regard of high temperature synthesis for solid states. Well, chalcogenates have been used or have been produced this way, but not too frequent before we started in this area. And all of the examples we found until we started was the use of separate sources for these molecules, for these clusters and complexes. And our idea, as I said, is that we use binary precursors to control or to also skip some kind of an oxidation step into this chemistry, and then added some further component, like, for example, tin tetrachloride in this case. And in this particular case, when we used these reaction conditions, 150 degrees C, so this is a reference to our very first paper in this field, but under a little bit varied conditions, we received a compound with this composition. And you see that the imidazolium cation went into the compound, so it replaced the potassium ions used initially. And this is very important and instrumental to this chemistry, that the ionic liquid cations play a role. It's not just a reaction medium, it's also a reactant. And these were nice red crystals, which turned out to have this crystal structure here. And just to have a previous view on this crystal structure, you can see that everything that is anionic, a very complicated formula though, is drawn in green here. So these ball type anions, and we have the pink cations in between. And if you analyze the structure of this compound, you will find that it's absolutely isostructural, just generally isostructural to sodium chloride. So very complicated and larger in scale, but the overall symmetry is like in sodium chloride. And you see that the color is different, so you would call it maybe a super sodium chloride, but you would probably not taste it because you see the elements will not be very healthy, so better don't. Let's get back to this crystal structure and just have a look at the initial anion. This is a very huge anion made up of 192 atoms. It's actually the largest main group element, polyanion, that has been reported, and it has a cavity inside with about 1 nanometer in diameter. And to explain the structure a little bit more in detail, here's the structural units that make up this cluster. It's a tin selenium-based and a germanium selenium-based structural unit. And to simplify these two structural building units, I just draw the group 14 elements now, which gives you this view. And if we just place a point of gravity or center of gravity here, then you will end up with a very simple topology. This is the C20 fullerene topology, telling us that this very complicated structure can be reduced to a very symmetric, very simple topology, which is kind of a beauty in this field, that you can reduce it to, or say nature loves symmetry, and this is what is reflected here as well. We can also use this cavity here for doing chemistry, like in some kind of a nano flask, which is shown here. You take the red crystals and soak them in a solution of iodine in cyclohexane. And over a time span of 3 hours, you will see a fading of this solution, and the color turns brown. You see this better here. And what we have found is that we form triiodide. So we have a heterolytic iodide bond cleavage and form triiodide here this way, which tells us that this is a pretty reactive compound. Well, getting back to the structure, we recognize that, and I also told that these counter ions played a role in this structure. And the question was, can we have an impact of these cations when changing them and exchanging them? So we played with these imidazolium-based counter ions, and this is what we do. We replace this alkyl group here. So this CN ligand can be replaced easily by just normal organic syntheses. And we tried a couple of different alkyl-based imidazolium counter ions in our ionic liquids. And this is the result of some of these experiments, which told us that we have always the same anion. So this ball type, zeo ball, how we call it, anion, does not change. It's just the packing mode that changes. So the ionic liquid cations just control the packing, which was kind of disappointing since we wanted to see an impact, templating effect of this counter ion, which is so much involved in the structures. But then we had to change the system. This was how it worked. And so we go from tin selenium now and germanium selenium to mercury and tellurium. Here, the substructure that we are reacting is not molecular. It's a polymeric strand. And you can see that in this little slide, under this little structure diagram, that we have a zigzag chain of mercury and tellurium. And we react these or treat them in ionic liquids, which have the same general structure, but we have different chain length: ethyl group, butyl group, hexyl, octyl, or decyl and dodecyl. And the results showed us that in the short chain alkyl chain ionic liquids, we get a monomeric unit. So we just split this zigzag chain, or we have a partial oxidation of neighboring tellurium atoms to form these 5 rings. And then we have a one-dimensional strand. getting to this longer chain imidazolium cations, we find this kind of a cluster molecule. And the special thing here about this cluster is that we have a methylation on the terminal ligand, which was absolutely unexpected. So we have a non-innocent ionic liquid, and I'll get back to that in a moment. And the reason why we form exactly this cluster is because it fits perfectly into the counter-ion sphere of these longer alkyl chain imidazolium cations. Last but not least, we took decyl and dodecyl chains, and so here you see the counter-ions, and what we got is this one. And this was, again, disappointing in the first moment, since you see that there is a structure relation with this trend here. And we thought, okay, so all templating effect is gone, and there is nothing to talk about. Yet when we grew the structure, we saw that it's actually not a strand, but it's a molecule. It's a discrete molecule with an 8- charge on it. And we find this situated within a lamellar structure. You see these long alkyl chains here separating the anionic layers from each other, and 8 imidazolium groups would compensate for the 8- charge of this molecule. You see that the molecules are a little bit distorted, so they just fit within these imidazolium groups, and this is why this structure seems to be extremely stable. It is the second known, I call it a perfluorinoid inorganic cluster molecule beside the simple structure of bore disulfide, as we found out, but this is a neutral compound, so you find a flat molecule here in this kind of compound. And of course, the dimensions are much larger with mercury and tellurium, so if you compare, it's nearly double the size, and this is a scaled representation of the atoms as well. And of course, we find the structural relationship with porphyrin itself. So here you have the structure of tetraphenylporphyrin, and you see it again that the dimensions are very different, but the overall topology is exactly the same. So what we looked after in this case is, do we have a similar electronic situation as well? So we asked ourselves, can this inorganic molecule be aromatic? So aromaticity means that you have a planar symmetric cycle, a macrocycle, if you will, and that the electron density is not fully localizable. So these are two preconditions for aromaticity, which should be fulfilled. There are some other preconditions, and you can look that up in the Gold Book of Chemistry from IUPAC, but these are the ones we are going to discuss now. So you know this very well from Kekulé's benzene, and this is how we represent aromaticity in chemical diagrams. And you can also simplify this for benzene with just this ring, and this ring represents a ring current that is formed if you take the molecule and place it within a magnetic field, where the pi electron cloud that produces this ring current, which is very inherent to all kinds of aromatic molecules. If it's produced in the pi electron cloud, you'll talk about pi aromaticity. If it's just within the bonds, then you will talk about sigma aromaticity. And so we calculated this compound, and we found out, first of all, that the anion turns planar. So without the counter ions, it's a planar molecule. So first precondition is fulfilled. Then we looked after the ring currents, and you can calculate ring currents very precisely. And here you are the comparison between porphyrin and this mercury telluride unit. And you see the difference. Very obviously, the porphyrin has a nice ring current going on, 1 Bohr above the molecular plane, while in this molecule, you don't find a really global ring current. What you find here is a weak local ring current, but it's in the sigma planes. And the reason for it is very simple, because we have much more electrons here. So this molecule is fully saturated, and it's not really fair to look after aromaticity in a saturated molecule. Yet we learned a lot during this chemistry. And here is a little excursus, because in the course of our chemistry, we asked ourselves more and more whether these metal clusters can be aromatic at all. And here I'll do just a little slip into simple chemistry and talk about something that is connected to multimetallic clusters, because there are known pi aromatic metal cycles, and these are all that have been known so far. So triangular, square type, and pentagonal rings with exactly these elemental combinations and charges. These turned out to be pi aromatic, but all of them have been included in much more complicated clusters or complexes. So they have been shielded and decorated, protected from further decomposition by ligands usually. So our case study is different. So we tried to stabilize these molecules from inside to have the aromatic and the ring current accessible from outside. And the case study included 2 multimetallic clusters, which are given here as their formula. They are anionic and have no ligands. And they were approached by using an F-block complex, these CP derivatives, along with a zintal anion called bismuth 4,2-. And by stepwise replacement, and this is a calculated mechanism here, we found that a cluster is formed that we could also isolate as crystalline materials. So here you have an X-ray structure diagram. And if you look at it from a side view, you'll see that this is a donut type molecule. So it's like a ring of bismuth atoms surrounding this inner thorium atom, which stabilizes the compound from inside. And to find out about aromatic properties, what you have to do is that you have to look after the the molecular orbitals. And what I'm displaying here is the so-called HOMO, so the highest occupied molecular orbital that is hosting exactly 2 electrons. And you see that this is the thorium atom inside. So you see that the thorium atom does not contribute, but all bismuth atoms contribute to this HOMO. And this caught our interest. We thought if all of these bismuth atoms are involved in one orbital, maybe it's not localizable, and so you can look after ring currents. And this is actually what happens if you try and localize this. This is a mathematic procedure. This is well known. And if you are looking closely to what I just did, I just moved from the HOMO to the so-called LMO, and this is the LMO, the largest energy expectation value, so the highest LMO, if you will. You see not a big difference. It's a little bit different, but not too much. So that tells us that all atoms are actually involved after localization, so it cannot be localized. This is, in contrast, something that happens with all other molecular orbitals. They can be localized, they will be situated between 2 atoms in the end. And this is the big difference. So we have one molecular orbital that could be starting our basis for a ring current. Okay, we calculated that. We exposed this molecule in theory to a magnetic field. And what comes out of these kind of calculations is a number. And here you are the numbers that we calculate for benzene or for porphyrin. Just take these numbers as they are. So this is nano ampere per Tesla. We have a number of 14 or 25 here for these well-known aromatic molecules. In our case, so we first found that we have a ring current. You see this again, 1 Bohr above the molecular plane. It is an integration box for it. And second, we can calculate a nice number. And this number is very similar to what we find for porphyrin. Yet, if you compare these compounds, we just use 2 electrons to get this ring current, while for porphyrin, we need 26 electrons. So the same kind of ring current strength is obtained, summarizing that this is not only the largest known aromatic metal cycle, it also displays the largest, or the record 2n plus 4 pi aromaticity per electron. So there are stronger ring currents calculated, but not with just 2 electrons. So in the end, you can ask yourself, is that something special? Maybe not, because it's a metal. And a very inherent property of a metal is that it can conduct electrons. So we should probably have expected that metal-like molecules and clusters are very good aromatic molecules if they have the precondition of being non-localizable. Well, just to give you some ideas of how this is going on, we are now looking into much more of these bismuth substructures, and we can form bismuth clusters with many different numbers of bismuth atoms. And I would like to just briefly mention one of them. This is the cluster that you've already seen on one of my first slides. It's formed from bismuth 2,2- and this very complex here. And the specialty about this compound is that it's a very regular prism. And you know that symmetry is always something that, sounds of being interesting in terms of aromaticity. And in second, it's relatively robust. So this is also a particular property of aromatic molecules, that they have a higher stability. And you see the robustness from the mass spectrometry. So this is a mass spectrum from the reaction solution, and you see just the molecular peak. So it seems to be very selectively formed and rather stable. You can transfer it into the gas phase without decomposition. And then if you check and analyze the molecular orbitals, you will find a very interesting molecular orbital that looks exactly like an orbital that you calculate for a hypothetic bismuth 6,2- cluster. So this is not known experimentally, but you can compare and see it's exactly the same. And now we come to symmetry. So this is an s orbital and a sigma symmetry of a molecular orbital. Here you have a p atomic orbital and a pi symmetry of a molecular orbital. And what we find here is something that we would refer to an F atomic orbital. So it should be phi type in symmetry. And as we found out that this is actually non-localizable, so we have this phi type orbital without localizability, we have also ring currents that we can calculate with reasonable numbers. And this is why we introduced this molecule as being the first one to be observed as a phi aromatic molecule. We also tried and calculated this for an organic counterpart, so prismane or prismen anion, and we found out very quickly that this does not work. This is not an aromatic molecule. You have no phi aromaticity here. So we need the metal, we need bismuth for it, and this was rather unexpected that bismuth would be a better aromat than something that is organic. And for this, it's easy to refer to a nice forum issue that we had on bismuth, the magic element. It can do pretty much everything you would like to have. And here I'd like to insert a little advertising break on behalf of Inorganic Chemistry, and you'll find links to some articles that may be of interest and also to the homepage of our journal and the scope of the journal in the chat in a moment. And here is just, we published a lot of fundamental studies, so it refers to what I've just been talking about. You have experimental studies, theoretical studies, all topics of inorganic chemistry can be found across the periodic table. And it's been published first in 1962. So last year we celebrated the 60th birthday. And you can see that it covers a lot of different aspects of inorganic material chemistry. The key metrics can be found here. So our impact factor is between 5 and 6 recently. And we published something above 2,000 articles per year, with acceptance rate of nearly 50%. We have a huge readership, as you can guess from the article downloads, and the average publication time is 12.1 weeks, sorry. Here's the team, and this is a group of fantastic editors that you'll probably be in contact with when you submit it to Inorganic Chemistry, and I hope that you made only very nice experiences with them, so all of them do a fantastic job. I'm really thankful to have such a great team at hand. We publish forum issues, we publish virtual issues, we publish viewpoints beside regular articles. So these are thematic collections, either in emerging topics of interest or emerging articles that have been previously published, which will be summarized in these kind of virtual issues. And viewpoints just gives us an opportunity to publish unique perspectives on exciting chemistry and emerging topics in a rather concise way. We are now introducing new types of articles. One of them is review articles, which will be a first for inorganic chemistry this year. And we have a new type of editorials that we will start with what is. That means that we are explaining things, pieces of interest, topics of interest in inorganic chemistry, what people have been discussing for a while or have been wondering whether there should be a new definition of something. And this is also something we would like to invite you to contribute to if you have a good idea. We will also be soon publishing dialogues in chemistry that go across boundaries and highly intersectional across, for example, geographic regions or careers or topics and so on and so forth. We also participate in the so-called lectureship program, which is in collaboration with the ACS Division of Inorganic Chemistry. And this recognizes individuals who've been demonstrating that they are extremely creative and have an impact in the field of inorganic chemistry. We get nominations from the research community and then have a selection committee that is contributed to from the editor-in-chief, the division officers, associate editors, and this editorial advisory board members, so rather broad. And here you see the names of awardees from the recent years, and you're the first one to recognize and get the name of the new one. So this is our first release of Alexandra Veljan being the recipient for the 2023 lectureship award. It is our great pleasure to award her with this in San Francisco in the ACS fall meeting. Well, this is all about the advertising block. So if you have any questions, please ask me after the talk. I'll be happy to answer all questions on inorganic chemistry in this regard. And now we're getting back to the ionic liquids. So after a little bit excursion toward multimetallic clusters and inorganic chemistry, we wanted to have soluble clusters. That was the initial intent. And the clusters I've shown you so far have been very highly charged, so they haven't been very highly soluble in terms of this ionic liquid chemistry. So But then we found out, and this was something that I mentioned only briefly, that ionic liquids can be non-innocent, producing methylated clusters. And we showed that this could also be done with selenide and sulfide clusters, not only with the telluride chemistry. And how that goes is shown here. So you take the imidazolium cation in your ionic liquid and you strip off one of the methyl groups that will just go to the terminal ligands and form the neutral imidazole, which we can show by NMR spectroscopy. So this is a relatively mild methylation method. If you think of some things like methyl iodide or merwine which are really harmful and toxic. And it is interesting to note, it is the only method to post-synthetically alkylate these kind of clusters. If you take any of the other methods, it will just not work. So there was two good things at once, and we dig further into that because with the methyl groups on it, the cluster is not yet soluble. So we thought of doing the same thing with selective butylation, and for this we needed to have symmetrically substituted imidazolium cation, because the butyl methyl one would selectively strip off the methyl group. Here it doesn't have any choice, and so the butyl groups go on the cluster, thereby reducing the charge from a naked cluster that has been described many years back from 8- to only 4-. And with the butyl groups on it, it is well soluble even in acetonitrile, which was unique for this kind of cluster materials. And we can show that these dissolved clusters are still intact, and we can look after the semiconductor properties of them. First of all, we had to prove that they are intact, and we can show it with mass spectrometry and NMR spectroscopy that they are retained in solution. And UV visible spectra tell us that the solid state spectra and the solution spectra are nearly the same. You will find roughly the same absorption properties and band gaps. So the semiconductor-like optical gap persists, and it can also be calculated. So we can take these clusters and just alkylate them a little bit to make them soluble, but keep their properties as semiconductors, which is maybe interesting for photocatalytic applications in the future. There is a second way of reducing the charge and making clusters soluble, and this is by aggregation. And here it's important to play with the precursor ratios. So what we have is the imidazolium cation from this ionic liquid, and then we add an auxiliary like this amine here, and we can play with its numbers and then get aggregations into dimers or tetramers or infinite zigzag chains. And of course, this affects two things. First, the solubility, and also the optical properties. And for the 3 molecular ones, we can see that the optical properties undergo a shift as expected with increasing cluster size. It's redshifted, and we see roughly the same behavior also for the solid state, and then including, of course, the zigzag chain, which has the smallest band gap. And you can see by mass spectrometry that you really have soluble clusters here. This, by the way, is the largest binary chalcogen methylated cluster, and it's soluble. So this was pretty nice to recognize. If we then go and even change the cations that we use in our precursors and change it for cesium, we see an aggregation of 4 of these clusters. So another type of tetramer, but here we have a cesium included in the cluster molecule. And this gives it first even a larger size. And second, it is even better soluble because it's an internal counter ion. And so the overall charge is just 7- instead of 8- with a larger number of atoms. So we can say that this is a very selective thing. None of the other alkali metals want to be in here for reasons of the fit of the sizes. And so this internal charge reduction gives it even a higher solubility. So with this, I'd like to switch gears for a very brief story on compounds where the alkyl groups that I've recently talked about or briefly talked about are installed from the very beginning. So we don't do that post-synthetically, but use it in the starting material. And that this way systematically produce hybrid compounds. And here is a little story about that. Because we were interested in installing sterol groups on clusters, and so we used a sterol tin trichloride, added a chalcogen source, a trichalcogenide source, and formed this kind of a cluster with 4 of these groups, sterol tin, and 6 sulfur atoms. This has been reported with phenyl groups many years back, but we wanted to have the sterol groups for having this functional part here for doing epoxidations or polymerizations or attachment to semiconductor surfaces. So this reaction was on one hand successful because we got a pure product, but it was amorphous. We couldn't get the structure from it. An air-stable powder, completely amorphous. So we took a mass spectrometry and confirmed the composition. We calculated the structure and saw that this is an adamantine type basis here. So it's very much related to the inorganic salts I've talked about. But we have organic groups on this adamantine type cluster core. And these groups are sterile groups, so they can be attached to semiconductor surfaces. This worked out nicely. But then we recognized that there is no inversion center on this cluster. And this caught our interest, since no inversion symmetry in turn means that it can have non-nuclear optical properties. So what we did is that we checked this, and what we expected was the second harmonic generation. This is what you get if you have a laser pointer with green light. Then you will have a red laser passing through an optical media somewhere here, and then you find the second harmonic being produced with the wavelength of green light. Well, actually, we did so. So we used a CW infrared laser diode. We sent that through our powder, and what we got is not the second harmonic, but a broad spectrum. We got a white light emission. And here you can see the chromaticity of this white light. This is the chromaticity of a black body emitter with different color temperatures. And here you have a warm white light color. You can also see that you can send the light through a prism and find a rainbow spectrum. And this spot here is exactly what you get at this dotted or dashed line here. This is the color temperature of a white light emitter or a black body emitter at the color temperature of a tungsten halogen bulb. So a warm white light halogen bulb. And we approached this spot by increasing the power of the laser. So here at this point, we have this spectrum, which is very similar. And it's a broad spectrum, as you can see. Here you have the dotted line. This is the spectrum of a normal white light LED. It's a bit more into the blue as known, and ours is a white light emission. This is very warm. And we can see that's a highly non-linear process. So you have a scaling with the electric field to the power of 8. And this is the speciality. We didn't use a pulsed laser for it. We just used a laser diode, which is some €4 or so, while this is an instrument that you can buy for 50,000 euros or dollars. And so this is the big difference, because broad emissions have been known, but they had to use this kind of instruments for it. So we don't need that. And the second new thing that has not been reported prior to our investigation was that the white light emission is directed. So here you have the directionality in space, very sharp directed of the laser. And the yellow part here is what happens if we have the powder of our compound on that laser. The gray sphere indicates the Lambertian emitter, which is isotropic and isotropic in space, so not directed. So this could be a new perspective for white light laser applications. And this brought us into a feeling that is pretty similar probably to what is shown in that picture here of that painting showing Henrik Brandt discovering white phosphorus, where he had this unexpected emission of chemoluminescence and didn't know what to think about it, because he was in search of the philosopher's stone, as all alchemists of his time. We know a little bit more about that now. We don't look for the philosopher's stone, but the feeling was pretty much the same, probably. Well, we digged into that subject much more deeply in the meantime and looked for different kind of ligands. I won't detail that too much here for the sake of time, but let you know that we found out that aromatic ligands and the missing long-range order, so the amorphicity, is needed for getting this broadband spectrum. Otherwise, if we have crystalline compounds, we will find the second harmonic generation, as we expected originally. We can fine-tune the spectrum a little bit by using different elements in our clusters. And we recently refined our preconditions in saying we don't need aromatic, but we need cyclic ligands. So it can also be cyclohexane, for example. But the rest, the missing long-range order, is a precondition that is absolutely necessary. The band gap must be in a certain range, so this is also very important. Well, and how that goes, how the mechanism is behind that, is still a mystery. We don't know about that, but we have now raised a so-called research unit from the German Science Foundation to find out more about that new property. Well, with this, I'd like to end my talk with a summary. I've talked about multimetallic cluster architectures and showed you a highly versatile approach to them. You've seen a lot of uncommon structures here, just two of them, and I've explained that we see templating effects of ionic liquids in this chemistry. We find very strange electronic properties, including, and this was a small excursion to this part, which I didn't detail too much in this talk, to multimetallic clusters. I've talked about reactive ionic liquids that take part in the reaction, alkylate, and lead to soluble structures. I've also talked about aggregation to form these soluble semiconductor cluster compounds in different ways. And last but not least, I've briefly mentioned clusters that have an organic group on them to form this kind of nonlinear optical properties. And something I didn't have time to talk, but just show it to you here, is that we can also use quaternary cluster cores, very inhomogeneous cluster cores, and form so-called cluster glasses, which have the same properties, but are much more easier to process. So with this, I'd like to mention that the main summary of our research is maybe that we go from fundamental research to what potential applications, as you've seen, and you can read about the diversity and the fun we are having in our labs in my editorial I wrote recently, and you find the link in the chat. So this is my contribution to this exciting kind of series of science talks. I hope that I could show you a bit of our fascination for this chemistry. And of course, I'd like to thank all the people who did this work. So this is my fantastic group, a lot of talented co-workers. I have very great collaborations going on, and a lot of funding is of course needed to make these people happy here. And of course, last but not least, I'd like to thank you for your kind attention, for giving me the chance. Thanks again to ACS India, especially, for giving me the chance to talk here today. And of course, don't forget to submit your manuscript, the next one, the nicest one, to Inorganic Chemistry. And with this, I'd like to thank you again. And now I look forward to take any questions you may have. Thank you again.